In this video, we're going to be jumping to Chapter 11 and starting to talk about statistical estimation and the sampling distributions. So we're going to start off by defining a couple of terms, one of them which is new to us, but one that we've used before we're going to define a little more specifically. And we're doing this because as we're beginning to use sample data to draw conclusions about a wider population, we need to be specific about the terminology that we're using. Remember, this is our first kind of foray into inferential statistics, where we're going to be learning how you can sample a small number of people to draw conclusions about the larger number of people. So we need to learn the statistical terms to distinguish those two. So the first one we'll talk about is a parameter. And a parameter is a number that describes some characteristic of the population, the entire population. And the thing that's important to realize here is that in statistical practice, the value of a parameter is not known because we cannot examine the entire population. When we're talking about a population for these purposes, we're talking about a very, very large number of data points. Maybe we're talking a very, very large number of people. And it's unrealistic to survey or ask or measure every person in that entire population. So we're calling that a population, and the parameter is some characteristic of that population, whether we're talking about the mean, height, or anything like that. But it's something we can't actually measure because we're not going out and actually doing the measurements on everybody. So that's kind of an important thing to understand. So the parameter is talking about the characteristic of a population, and we can't directly measure that because the population is too large. So we're going to be using inferential statistics to make conclusions about that parameter. The other term that we'll define a little more specifically now is that a statistic is a number that describes some characteristic of a sample. So sometimes we've heard people use the word statistic if we're just talking about one person's height. We're going to be a little bit more specific now and say that a statistic describes a little bit more generally some characteristic of a sample. The value of that statistic can be computed directly from the sample data because we've gone out and we actually have measured every person in that particular sample. We can compute the statistic. And we'll then use that statistic to estimate an unknown parameter. So for example, the mean is a statistic because it's a number that's computed about a sample. We're then going to be able to use that sample mean to be able to estimate or infer the mean of the population, which would be the parameter. So one way to kind of just remember the distinction between the two is statistics come from samples and parameters come from populations. But you can't, the other piece to remember there is, again, a parameter is not something that you're going to calculate about the population. The parameter, we're going to use a statistic about a sample to help us infer the actual parameter or estimate the parameter. So, just reviewing some of the terminology and the shortcuts, the variables, that we're using to indicate these words. First, talking about the mean. When we're talking about the mean of a sample, we use X bar to represent that. When we're talking about the mean of a population, we're going to use the Greek letter mu. So here we have X bar for the sample, mu for the population. When we're talking about standard deviation, a small s is what we'll use to describe for a sample. And the small Greek letter sigma is what we use for population. So we're going to talk about a few things here now with statistical estimation. And these are going to be kind of very important chunky statements. So I just want to take a minute to really digest each one of these and clarify what they mean. The process of statistical inference involves using information from a sample to draw conclusions about a wider population. So again, if we have 10,000 people and we want to know something about their heights, we're not going to measure all 10,000, but we could maybe measure 100 people's heights and then draw a conclusion about the heights of the entire population. The next statement that we want to talk about is this one. different random samples yield different statistics. We need to be able to describe the sampling distribution of possible statistical values in order to perform statistical inference. So let's break this down a little bit. So different random samples yield different statistics. Again, looking at our 10,000 people, if I choose 100 people and measure their heights and calculate the mean, and then I choose a different 100 people and calculate their heights and calculate the mean, those two means are probably going to be a little bit different. They're not, the means of every possible 100 people in that group is not always going to be exactly the same. However, we can actually create a distribution of all of those means, and that distribution will help us to perform the statistical inference about the height of the heights of all the people in that group. So again, every individual sample that we take has a different mean, and then if we plotted the distribution of those means, that's what's called a sampling distribution. And we'll do an example of that in a minute to make that a little bit more clear graphically. The third kind of big thought here, and that sort of traces back to what I just said, is we can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. Therefore, we can examine its distribution using what we learned in earlier chapters. So for example, we've been doing histograms and density curves, for example, of people's heights, where you would measure those 100 people's heights and you would then create a distribution curve of their actual heights. Now that we're going to be doing inference, what the distribution curve would actually be is we'll take the mean of this 100 people, the mean of the next 100 people, the mean of another 100 people, and plot the distribution of those means. And again, that will then allow us to start to use what we've done in the past to make inferences about the population. So the sampling distribution is not going to be a density curve of the actual heights of people. It's going to be a density curve of the means of all of the heights of the different samples. So if we took 1,000 different samples of 100 people, those 1,000 means would form our sampling distribution. So just to put in a little graphical picture of what we're talking about statistical estimation, we have a very large population, and we're going to learn about how we can take just one sample from within that population and collect data from that representative sample and use that data to make an inference about the entire population. But before we can get to the point of just taking one sample to infer about the population, we kind of need to understand a little bit about how that's even possible. That by measuring just 100 out of 1,000 people, we can draw some conclusions about the distribution of that 1,000 people. So to do that, we kind of have to understand this concept of sampling variability, and that's, again, the fact that the value of a statistics varies in repeated random sampling. And that gets back to, again, if I measure this 100 people and that 100 people and another 100 people, the statistic, the mean for all of those three sampling groups is not going to be exactly the same. It is going to be a little bit different. So we have to understand that. Maybe the first group had an extra tall guy in it and the second group had an extra short guy in it. So those means are not always going to be exactly the same, but that's okay. As long as we can understand, we can account for that variability. So to make sense of sampling variability, we're going to ask what would happen if we took a lot of samples. Again, we're going to get to the point where we're only going to be taking one sample, but to get there we have to understand what happens to taking lots of samples and how that, what we can learn from that to get us back to just taking one sample. So sampling variability, we're first going to look at taking that large population, but instead of taking one sample, taking lots and lots of samples and using that to infer something about our population. And to do that, we're going to learn about something called the law of large numbers. So when we ask ourselves, how can X bar, how can the mean of one sample of people, one of those groups of 100 people, how can that give us an accurate estimate of mu, the average for the entire population? especially because we now understand that every 100 people that we measure is going to yield a different value of mu. Well, if we keep taking larger and larger samples, the statistic is guaranteed to get closer and closer to the parameter of mu. So for example, if we have our population of 10,000 people, and we only measure 2 people and take their mean height, their mean height's probably not going to be very representative of the entire population. But if we take 10 people, or if we take 50 people, or if we take 100 people, or if we take 1,000 people, the more people we measure and calculate their mean height, the closer that mean of the population is going to get to the parameter mu. And so kind of stating that in formal terms, when we draw observations at random from any population with a finite mean mu, the law of large numbers says that as the number of observations drawn increases, the sample mean of the observed value gets closer and closer to the mean mu of the population. So that kind of makes sense. It kind of makes sense that the more people we sample, the more accurately we're going to be able to represent the mean of the population. Now, we talked about at the beginning of the course that one thing that we're going to be skipping is this sort of major concept in statistics called probability, which is a whole study unto itself, and we really don't have the time in this course to explore it in detail, but we do have to just kind of understand that it does form the foundation of everything that we're talking about. So the behavior of X bar, the behavior of the means of all of these samples that we're taking, is similar to the idea of probability. This whole process of inferential statistics is all founded on probability. In the long run, the proportion of outcomes taking any value gets close to the probability of that value, and the average outcome gets close to the population mean. So what that's really talking about is we've been talking about proportions and percents of people whose values fall within a certain number within a certain data point, or between 2 data points, or above or below a data point. We're going to use that same sort of concept and think about it now in terms of probability. What is the probability that X bar is close enough to the population mean for us to be able to use that? So this graph here just talks about the law of large numbers, and for one particular example that they use probability calculations, which we're not going to do. But just to show you that if this dotted line here represents mu, that for some reason we have a population that we do actually know the average of, we actually do know the mean of the population. If we take samples, if we take one sample, we can see that the mean is pretty far away from the population mean. If we take, this looks like maybe 3 samples, it gets a little bit further away. But as we take greater and put more and more people into the sample that we're measuring, eventually our sample mean starts to get very close to the population mean, close enough that we're able to then use that to estimate the population mean. And again, this is all about estimation, inference, not proof, not actual measurements. This is using probability theory to say that if I have a large enough sample size, then probability says that the sample mean is going to be very close to the population mean. So as we talk about sampling distributions, we've talked about the fact that if we measure enough people in a sample, the statistic X bar gets us closer to that unknown parameter of mu. But what happens if we take every single possible sample of a certain size and calculated the sample mean for each and graphed that? We'd end up with a sample distribution. So again, if we had 10,000 people and we said, well, we know the law of large numbers says we want a good size sample, and 100 people is going to give us, according to the law of large numbers, a good enough sample to estimate the parameter. I'm not just going to ask 100 people. I'm going to ask every possible combination of 100 people within that population. This is just a theoretical thing, not something that you would ever actually do in life, but this just gets us to the concept. What would happen if we calculated the means of every combination of 100 people possible? So we have our group of 100 people here. In this case, we're going to do samples of size 10. So, again, theoretically, you wouldn't know that of these 1,000 people, the mean is 25. But just from an academic perspective, let's say that we know that mean is actually 25. So we take a sample of 10 people, we get a mean of 26.42. We take another sample, we get a mean of 24.28. We take another sample, we get a mean of 25.22. If we did every possible combinations of 10 people in that group of 1,000 people, and then created a histogram of all of the means, not the values of, say, the height of every one of these people, but the mean values of height of all of those people, that histogram becomes our sampling distribution, or that density curve becomes our sampling distribution. And sampling distributions will take on a normal distribution. Because of the fact that, there is, if you're measuring something that the sample is approximately normal, like heights, we know that the data is not going to be skewed, then the sampling distribution is also going to follow a normal curve. So again, this sampling distribution is not the heights of all the people, it's the mean heights of each group of 10 people that we sampled. And again, that's going to show us that most of the people have the same heights, but there are some taller people and some shorter people. So it's key to remember that the sampling distribution is the distribution of the means of all of those samples, and that distribution is approximately normal. And the fact that that distribution is approximately normal means we're going to be able to take all that we've learned about normal curves so far and use those to help us to infer information about a population just by measuring a sample. So just to get a further distinction here, the population distribution is a distribution of all of the values among the individuals in that population. So if we were to actually graph the heights of all of those 1,000 people, that would be a population distribution, describing the individuals that make up the population. The sampling distribution is a distribution of the statistic of all of those samples, and the statistic you'll generally use is the mean. For example, the distribution of all the means of the samples, and the sampling distribution describes how a statistic varies in many samples in a population. They'll mostly cluster around the middle, but there'll be some high and some lows. So, to show this again graphically and to kind of talk about the three distinct distributions involved when we sample repeatedly, the population distribution is about the values of all the individuals in the population. The distribution of the sample data shows the values of the variables for all of the individuals in the sample, versus the sampling distribution shows the distribution of the statistic value. So notice the difference in number 2 and 3 here. The distribution of sample data would be the distribution of the actual heights of the people in the sample. So that's the distribution of the sample data. The sampling distribution, it does sound very similar, but it means different things. The sampling distribution is the distribution of the statistic. So the distribution of the means of the different samples that you took within that population. And to kind of describe that, if we were to just ask a population, what's your favorite color, blue or red? And again, for some reason, theoretically, we actually know what the population distribution is, and that's showing that half the people like blue and half the people like red. Well, if we were now to take samples of the people in that population, so we know we have 200 people who are in our population because we have 100 blue and 100 red. So now here we're going to take samples of size 20, and we're going to ask each one of those samples of 20 people, what's your favorite color, blue or red? And as we calculate the mean values of those, they've done some conversion from blue to red to numbers. We can see that the sampling distribution is approximately normal, and that's going to allow us to, in the future, draw some conclusions about the population.